This is the next to the last podcast. Unless you're going on to AP, in which case there will be more. Now, this is all about how do you make reactions go faster or slower, and also how do you know if a reaction is going to happen at all? What governs whether one thing burns and one thing doesn't? What makes one reaction happen very readily and one thing not happen very readily? So let's get to it. I think we can all agree that there are two trends in nature. Everything goes from a situation of order to disorder. For example, there's a pile of leaves, the leaves get scattered. Your room goes from being clean to being dirty. All those kinds of things. We go from a state of lots and lots of order, like your body, to lots and lots of disorder, your body dead when it gets eaten by things. We also go from high energy, meaning really, really useful energy, to low forms of energy. Okay, those are two trends in nature. So really, really useful energy, not very useful energy. Some reactions we call exothermic because they give off heat. Some reactions we call endothermic because they take in heat. The exothermic ones make their surroundings hotter. The endothermic things make their surroundings colder. Obviously, fire is exothermic. Things that are cold, if you've never tried it, try like baking soda and vinegar. That's an endothermic reaction. Those cold packs that when you buy them in the store, you break them, you snap it, and you shake it, and it gets really, really cold. That's another example of one. This is a reaction. One of them is exothermic, and one of them is endothermic. You have to figure out, is the blue one exothermic, or is the green one exothermic? Well, the blue one starts out way up here and ends way down here. So that's starting from this energy and losing a bunch of energy. That's exothermic. Endothermic, you start here, down here at the bottom with the green one, and you go all the way up here to the top. So it actually gains energy over time. A good example of this is cellular respiration, where you release energy from the food that you eat. And this is photosynthesis, where you take the same things that you end up with from cellular respiration, CO2 and water, and you use sunlight, and you store that sunlight energy as sugar. They're exactly opposite of each other. Delta S is the symbol for entropy, and entropy is just disorder in a system. Delta S is the amount of change in entropy. If you have a positive change in entropy, that things are more disordered, and so a negative change in delta S is going to be less disorder, and another way to say less disorder is more order. So we can talk about things in terms of gaining entropy or losing entropy, just like we can talk about gaining heat or losing heat. You guys try and figure out which one has more as you watch the podcast. The answer is gaseous carbon dioxide, because a gas always is much more disordered than a solid. It's much more spread out. The key here is to look at the pressure. This is a high pressure. This is a low pressure. How do you get high pressure? You get high pressure by taking the volume and smushing it into a small volume. So as the volume goes down, the pressure goes up. If you have gas in a small container, that's much more orderly than gas in a really big container, because you've got it more ordered. It's in a smaller container. You guys need to predict, is it positive or negative for each situation? Positive. Negative. Negative. You're turning a liquid into a solid, so it's more orderly. Liquid turns into a gas. Positive. Then the last one is a function of Gibbs free energy. And Gibbs free energy is very simply put, it's just something that tells us whether a reaction is going to be spontaneous or not. That's all you need to know. If delta G, when you calculate it, is negative, then the reaction is spontaneous. So like a fire is spontaneous. If you burn down a house, it would have a negative delta G for the reaction. But the reverse would not be true. If delta G is positive, then it's non-spontaneous. Burning down a house, right here, that's spontaneous. The opposite of that is non-spontaneous. You can't take ashes and carbon dioxide and water and stuff and you can't turn it into a house again. It doesn't work that way. If the delta G is 0, that means the reaction isn't really happening. It's not going anywhere. It's just sitting there. And so anytime you have a delta G of 0, it tells you that you're at equilibrium. I'll probably have you work maybe one of these, but the whole point of this is if you can find delta G, you can determine whether or not a reaction is spontaneous or not. Delta H is the heat either released if it's exothermic or the heat gained if it's endothermic. T is temperature, and delta S, of course, is entropy. Kinetics, you want to talk about how fast does a chemical reaction happen and how can you make it faster. So y'all can look these things over. Every reaction has what's called an activation energy, the energy necessary to get it started. You can see you're starting out here and you have to climb that hill. That hill right there, that is the activation energy. Every reaction has an activation energy. Sometimes the hills are small, sometimes they're tall. It's just a function of how easy is it to get that reaction going. These are all examples of things that need activation energy. Matches, they don't need much because all you have to do is rub them up against something. Paper is actually pretty hard to burn. You can't just rub it between your hands and get it hot enough. You have to actually do something with it. The magnesium and acid do you have to do anything to it? Not really. I mean, when y'all dumped magnesium and acid in lab, it works. So you throw it in there and it works. So it doesn't need it to be hot or to add in a bunch of energy. Burning magnesium, though, you need a lot of activation energy. Y'all actually burned a strip of magnesium. You weren't supposed to look at it. It was very bright, right? Well, you can't just light it with a candle. You can't just light it by setting it out in the sunlight. So that requires a lot of activation energy. And then paper and water, of course, wet paper won't burn. You can't burn paper that's wet or in water. So it's going to have a super, super high activation energy. The activation energy is so high, it just won't ever happen. All a catalyst does is it lowers the activation energy. This is without a catalyst up here in blue. This is with a catalyst down here in red. It just makes it easier for a chemical reaction to happen. It doesn't change where you start at and where you end at. It just makes the hill a little bit easier to climb. This is the way I like to explain these things of catalysts. So if you read these statements, 7th graders, boys are way afraid of girls. Bo will never talk to Susie, and since Bo will never talk to Susie, the activation energy threshold is way too big. It'll never happen. A reaction, a relationship will never happen. But in every class, there's always somebody named Pat. And what does Pat do? Pat goes around and gets people together. She passes a note. In other words, she provides an alternative route for the reaction. She makes it easier for the reaction to occur. So this is just a sample problem that you might work with delta H, with enthalpy, with a reaction that's either endothermic or exothermic. So let's take a look. You got some hydrochloric acid, all right. You got some sodium hydroxide, all right. That sounds okay. Temperature changes, all right. So this goes all the way back to the beginning of the year where we did calorimetry, where we figured out the number of calories in food. So let's use that same equation here. It's MC delta T, right? The Q is equal to MC delta T. And it's the grams, which is 50 and 75 is 125 total. And the C value for water, which is pretty much just water, is 4.19. And then times the delta T, the change in temperature. So we do that. And it's 2.83 kilojoules. Now, the whole question is, though, is this negative 2.83 or is this positive 2.83? So how would we write the delta H for this? Negative or positive 2.83? Well, it got warmer. So if the solution got warmer, then what did the chemicals have to do? Gain heat or lose heat? If it gained heat, wouldn't it have gotten cooler? That's right, it lost heat. Very good, I knew you'd get it. The delta H for this should be negative. And that's pretty simple. So if you look at this chart real quick, exothermic, losing energy. If we actually had numbers on the y-axis on the two diagrams, we could actually calculate the delta H there, but we don't have them. But one loses heat, one gains heat, and so that makes sense, right? Molar enthalpy is delta H per mole, just like we would have molar mass, right? We could describe mass, or we can do molar mass, the mass of 1 mole. This is the delta H, the kilojoules per mole. Predict the change in enthalpy due to the combustion of some propane. It tells you how much per mole it is. So what would your plan of attack be? No, you don't give up. No, that's not it. No, you don't guess. No. That's right. Your first job, since it's in kilojoules per mole, is to change grams to moles. Very good. And then what's your second job? That's right. To use the component of the negative 2043.9 kilojoules per mole. And we can do that using dimensional analysis. And there you go. We change grams to moles, and we use the fact that was given to us, and that's the delta H. That's how much heat is released when you burn propane. All right, now once we have delta H, we can start communicating that bad boy. Here's an example. We know that the delta H for this sucker is negative 725.9. Now, does that mean that heat is a product or a reactant? That's right. That's a product. So where would we write that delta H at? Where would we write that number at? Where would we write 725? And I'm going to guess that we would write it on the right, because 725.9 kilojoules is a product. Heat is lost. That means heat is given off to the environment. So we'd write it over there. All right, here's one more example. This has got 285.8 kilojoules on the left-hand side. So if it's on the left-hand side, what do we do? Well, does that mean it's endothermic or exothermic? Well, if it's on the left-hand side, that means heat is a reactant. Energy is being absorbed. So if heat is a reactant, what is our delta H going to be? Our delta H is going to be positive, because heat is a reactant, 285.8 kilojoules. It was just that simple, because from the equation we know heat is a reactant. That's it. Slide down to this one down here. What are you seeing down here? Well, heat is a product. So what do we do for this one? Well, if heat is a product, then the delta H is just going to be negative 601.6 kilojoules per mole. All right, so if you look at this equation right here, we know the delta H is a positive 136.4. What do? Do we put it on the right or the left? Vote. Right, left, vote. And now, look at the answer. True enough, we do put it on the left. Why? Because delta H was positive. That means heat is a reactant.